5.1 is randomness, probability, and simulation. It's really pretty short and pretty sweet. 3 objectives: describe the idea of probability, describe the myths about randomness, and design and perform simulation. The idea behind probability, what is probability? It's basically chance behavior, and chance behavior is unpredictable. It's unpredictable in the short run, but it is regular and predictable in the long run. Chance behavior, it's unpredictable in the short run, but it's regular and predictable in the long run. So if you flip a coin, it's like chances are that you get a heads or tails is 50-50. But to really say in the short run, I flip this coin, what am I going to get? Who's to say heads, who's to say tails? But if we go through and we flip a coin like thousands of times, what happens is we might get a bunch of tails first, and then we might get a bunch of heads in a row, and then we get a bunch of tails again. But after time, as time goes on, if you find the average of each of those probabilities and average them all together, eventually it'll approach, it's a 50-50 chance of getting heads or tails. But in the short run, you flip a coin, it's like, who's to say whether it lands on heads or tails? Probability is a number between 0 and 1. 0 means it never occurs, and 1 means it always occurs. And that's kind of comparable to saying between 0% and 100% of the time that occurs. It describes the proportion of times an outcome would occur in a very long series of repetitions. The law of large numbers says that the proportion of times that a particular outcome occurs in many repetitions will approach a single number. Proportion of times that a particular outcome occurs in many repetitions will approach a single number. So if you flip a coin many, many times and record all those results, after so long, after 500 trials, after 1,000 trials, eventually you'll see it's pretty close to 50-50. If you roll a dice, what's the probability that a 1 occurs? If you do it thousands and thousands of times, probability that you roll a 1 would be 1 out of 6, a 1 in 6 chance, right? So this is what happens with law of averages. However, there's some myths about randomness, and this one says, so the law of averages doesn't guarantee me a girl after 7 straight boys, but can I at least get a group discount on the delivery fee? We'll talk about why that's kind of goofy in a second here. The myths about randomness, the first one is the myth of short-run regularity. And I know we've written it about twice already, and we're going to write it again, but the myth of short-run regularity basically says this: we can't predict in the short run. We can't predict in the short run. The idea of probability is that randomness is predictable in the long run. And I know I keep saying that, but I can't hit that hard enough. And we've already talked about why we can't predict in the short run, but we can in the long run. And the myth of the law of averages, the myth of the law of averages, probability tells us random behavior evens out. In the long run, it evens out. It's like it approaches 0.5 of heads versus tails. Future outcomes are not affected by past behavior. That is, past outcomes do not influence. Past outcomes do not influence the likelihood of individual outcomes occurring in the future. And if you want to listen here real quick, on page 289, there's an example about people having babies. Don't fall for the law of averages. Belief in this phony law of averages can lead to serious consequences. A few years ago, an advice columnist published a letter from a distraught mother of 8 girls. It seems that she and her husband had planned to limit their family to 4 children. When all 4 were girls, they tried again and again and again. After 7 straight girls, even her doctor had assured her that the law of averages was in our favor 100 to 1. Unfortunately for this couple, having children is like tossing coins. 8 girls in a row is highly unlikely, but once 7 girls had been born, it is not at all unlikely that the next child will be a girl, and it was. So, law of averages, you're like, oh, it should even out. Maybe in the long run you'll get a boy in there, but the law of averages is a myth. It doesn't necessarily even out. Oh, I've had 7 girls, it's time for a boy. Well, the 8th one was another girl, okay? Simulation, the imitation of chance behavior. Simulation is the imitation of chance behavior. Bless you. Based on a model that accurately reflects the situation. And we'll look at an example of a simulation in a second. To perform a simulation, we always go through the state, plan, do, and conclude. So the first thing when we state what is the question of interest? That's always the same. What's the question of interest about our chance process? With our plan, we describe how to use chance device to imitate 1 repetition of the process. So we clearly explain how to identify the outcomes, how to identify the outcomes of the chance process, and what variable to measure. And I'll show you in a second here. And then when you do simulations, the key part, and this is so important, is that we perform many repetitions. You perform many repetitions of the simulation, and then you draw your conclusion. So we can use physical devices. You can use your random number table of random numbers, and we can use the calculators to do that, or you could use the computer. Excel could do that for you too. So first of all, here's an example of a simulation. At a local high school, 95 students have permission to park on campus. Each month, the student council holds a golden ticket parking lottery at a school assembly. The 2 lucky winners are given reserved parking spots next to the school's main entrance. Last month, the winning tickets were drawn by a student council member from the AP Stats class. When both golden tickets went to members of that same class, some people thought that the lottery had been rigged. There are 28 students in the AP Stats class, all of whom are eligible to park on campus. Design and carry out a simulation to see if that's possible. You got a school of 95 students that can park on campus. They conduct a simulation and draw 2 tickets to say, hey, these 2 people can park in reserved parking. The person drawing those tickets was from the stats class, and both of those people that were selected were from the stats class. So they're like, oh, it's a little fishy here. What's going on? So the first thing that we do is we state the question, which they already did. They said, what is the probability a fair lottery would result in 2 winners from the AP Stats class? So the second thing we do is we define, well, what are we trying to measure, and what are our labels? So like for the AP Stats class, we have students 0, 1 through 28, because there's 28 students. And then you have the other, which is 29 through the 95 for the 95 students total. And then all the other numbers, 96 to 0, 0, we skip. So they took row 139 from your table D in the back of your book, and they put it all right here. So we look at pairs of digits until you see 2 different labels from 0, 1 to 95, and record whether both members are of the AP Stats class. So if we have 55 and 58, are these AP Stats students? No. So in here we're like, this one doesn't work and neither does that one. And that's a bad color. This one doesn't work and that one doesn't work because they fall in the other category. So I'm looking, how often does it occur that both members are in the AP Stats class? 89 and 94? They're neither. I have 04 and 70. 04, that is a stats student. But 70, that is not a stats student. So this is a no, that's a no. 70 and 84, both of those are other students. And again, I'm looking for 2 stats students. 10, is that a stats student? Yes. 98? 98 is in here, so we skip it. So I'm just going to put like skip. And then 43, is that a stats student? And this one doesn't work because I need 2 check marks. I need 2 AP Stats kids. Here, 19 and 12, those are both AP Stats students. So here it does happen. No. So how many successful trials did we have? This one works, and this one works, right? And so down here it says, based on 18 repetitions of our simulation, both winners came from the AP Stats class 3 times. So the probability is estimated as, we had 3 out of 18 trials, 3 divided by 18, what percent of the time is that? 16.6. Repeating, so like 17%. So 17% of the time, the 2 winners actually did come from this AP Stats class. And let me just kind of run right back through this one more time. It's like we're drawing two numbers from a hat, and we want to know, are those AP Stats students? That's like one simulation. And then we did it again. We put those numbers back in, and we drew 2 more numbers again. And this is like our second trial, our second simulation. And then we did it again, and we're like, so we did this 18 different times. We could have done it 30 different times if we wanted to. And then you go through and you count how many times did we get both winners are from the AP Stats class. What we had were 3 out of our 18 trials. Maybe you get 5 out of 30 trials, and each time it might be a little different percent, but just roughly close. So for this to occur 17% of the time, is it completely unheard of? 17% isn't a lot, but that's not completely unheard of. So it's possible that their trial that they did when they drew 2 stats students, it's possible that that worked.